Welcome to week 6, week 5. Sorry, I'm getting ahead of myself. As usual, we'll start with a glance at the schedule. So here we are, week 5. We're starting input space coverage. So we're actually starting today. Up until now, we've kind of been covering a little bit of this, a little bit of that, kind of jumping around to different topics. Topics that we need to have in our toolkit, but now starting this week, we're really getting into the heart of the class, and we're pretty much going to be spending the rest of the semester on testing criteria. So we're going to start today looking at input space coverage criteria. So that's today's work. Next week is a little different from all the other weeks in the semester. Next week will be an entire class-long extended in-class exercise on input space coverage. So you have that to look forward to next week. Also next week, assignment 3 is due. I've had a couple of emails on assignment 3. There's been a bit of discussion in the Blackboard forum on assignment 3. I encourage you, rather than emailing me, if you have a particular question about your work, then yeah, email is appropriate. If you have a question that you think other people might benefit from, then the Blackboard forum is really the place to ask that, so that everybody else can benefit from your question, from the answer. So there have been 1 or 2 answers in there, so check that out. Also, last week, as we were talking about test doubles, I did mention that the test double example that I had was still JUnit 4. It hadn't been updated to JUnit 5 yet. I've now updated that to JUnit 5. I revised the slides. I also put a different example, but the prime number factoring example. I put all the code for that using JUnit 5 and an updated version of JMock. I put all that in the forum discussion as well, so that you've got a decent example, a current example to work from. Let me put it that way. The old example was not incorrect. It was maybe just a little dated and not entirely consistent with the current version of the tools. All right, so you have those new resources out there for you. With that, we'll ditch the syllabus. And let's pick up our quiz review for quiz number 4. Overall, great grade distribution on quiz number 4. Good job, folks. Just about everybody seemed to have a really good handle on this content. So I'm gonna kind of really breeze through the review here, but we talked about advantages and disadvantages of dependency injection. The big disadvantage of dependency injection is that it increases coupling or decreases encapsulation. Is my audio a problem for folks? All right, stand by 1 second. I'll reset my headset. Okay, radio check. How's this? Is this any better? Okay, good. Thanks for letting me know. All right, so dependency injection, the major disadvantage is that it really reduces your data encapsulation, or alternatively increases coupling. It forces more knowledge of classes that are used by other classes. And that's a significant disadvantage. What's refactoring? What are some of the benefits? So when we're refactoring, we are changing the internal implementation without changing the external interface, right? So it looks the same to all the users, but the internal implementation has changed. Why would we do that? We might do it to improve performance, especially to improve maintainability, and just kind of to clean up the code, right? Just make it neater, easier to maintain, easier to manage, more reliable. A lot of multiple choice questions. I'm not going to go through these. There are many more than even just these. This is just a sample of them. You can see all the answers in the quiz. Wouldn't renaming the interface methods also be a refactor? I would argue that that would not, strictly speaking, be refactoring, because now we have changed the external interface. Is it a major change? Not really, but it does force changes outside the unit, outside the class. So I would argue that, strictly speaking, that would not technically be refactoring, because it's making a publicly visible change.
My argument, though, is that any changing that would be under like any IDE's refactoring suite of tools.
Mm-hmm. Well, and the nice thing about using an IDE for that, you can make it propagate all the changes out, at least to all of the code that's in your workspace that it knows about. There's still the risk that there's other code that's not in your workspace that isn't going to be automatically changed by your IDE. So the IDE isn't a magic answer to that, but boy, it sure helps. But technically, by the agile definition of refactoring, which is keeping the interface the same, I would argue that's not technically refactoring. All right, and subsumption, there were a couple of different forms of this question, but they all boil down to basically the same thing. One test criteria subsumes another if every set of test cases that satisfies one is guaranteed to satisfy the other. Bugwart's House Cup. Little bit of a shake-up. The Muggles' big lead is kind of shrinking. Ravenclaw is right behind, and I think the big change on the board has really been the Gryffindors, who have finally gotten out of the starting box here and are doing a good job of catch-up. So it's working out to be a very, very interesting early semester run here. All right, let's switch into just a real quick review of assignment number 2. Assignment number 2 scores, again, overall pretty good. Lots of 10s. You should be able to see this in Blackboard as well, but this was the expectations and the grading guidance for the assignment. So this is feedback that you get to understand what the grading was, and also to check your grading against this and just make sure that you were graded appropriately. I don't really have I don't have an example set of tests here. I don't have example code because there's so many things that you could do. What I do have is the error and the corrected versions of Cal. So here's the Cal source code. The red lines are lines that were in error, and the blue lines underneath them are the corrected lines. So we had five different defects that were injected into Cal. This first one, this is a pretty easy one to find. Day 2 mod day 1 instead of subtracting. Basically, any test of 2 days in the same month is going to find that. A little more subtle. Wrong number of days for, I think it was August. So you would have to have had a test that spanned over the end of August in order to catch that. Little logic change in the leap year the leap year computation. So these are the changes that were in there that were available for you to find with your set of tests. All right, so any questions or discussion about the quiz or that assignment?
We're never going to see the grade for the assignment.
Is the grade for the assignment not currently visible?
Let me double check.
Yeah, I saw it on mine when I checked like an hour ago.
I'll check right now.
Yeah, it looks like it should be.
Oh yeah, I see it, yeah.
Okay, great. All right, so let's dig in. Like I said at the beginning, now this week we're kind of transitioning. We've been hitting kind of scattershot, hitting a couple of different topics that we sort of needed as a foundation for the work that we're going to be doing. But now we're really diving into coverage criteria for the rest of the semester. Usually, for the most part, going to be spending typically 2 weeks per type of coverage criteria, right? Per class of coverage criteria, if you want to look at it that way. So this week and next week, we'll be dealing with input space coverage. So, you know, in the topic of software in the news, this isn't new news. This was news a year ago when, well, no, 2 years ago, actually. But it's such a great quote that I decided to keep it. So 2 years ago, early 2020, Boeing had their first flight of their Starliner spacecraft. The first flight went poorly due to a number of problems with thrusters and some other things. And here's the great quote. This was NASA program manager, I think it was. The bottom line is that industry is very bad at doing software, which is something that we should all kind of look at and think about and look in the mirror and figure out what part of that we play. But that forced Boeing to do a very expensive second unmanned test flight, which they weren't planning to do. And that unmanned test flight has been delayed and delayed and delayed as more and more problems were found. It finally launched earlier this year, and a crewed launch isn't planned until early 2023. So this was basically a 2-year delay, a 2.5-year delay to the program from that first test flight. All right, so here's the graph we're going to be looking at every week, right? This is basically the kinds of, the green boxes are the classes of coverage criteria that we can be using. And this week, we are starting out here over in input space. So what are some benefits of input space coverage or ISP input space partitioning? First of all, it can be equally applied at essentially all levels of testing. This is a technique you can use for unit testing, a technique you can use for integration testing, for system level testing. Whatever kind of testing you are doing, this is an appropriate approach. Not the only appropriate approach, but an appropriate approach. It's relatively easy to do input space partitioning without a lot of tools or automation. And it's typically an easy one to adjust to get more tests or fewer tests. You also don't really need implementation knowledge, right? So from our older terminology that we've used in the past, black box versus white box, this is very black box testing. I don't need to know the system internals in order to do input space coverage. So what we want to do in input space coverage is identify the entire domain of each particular input, and then break that domain up or partition that domain into different blocks. And we want to take the domain, we want to partition it into a set of blocks, and we want to satisfy two properties with that partitioning. When we partition the domain up into blocks, the blocks must be disjoint. There have to be no overlaps within the block, no overlaps between the blocks. What that means is that any particular value for this input can only fit into one block. It can't fit into two. And the blocks must be complete, which means that together, the union of them must cover the domain. So there's no possible input in this domain that doesn't belong to one block. Another way to look at this is that every possible input must belong to exactly one block of the partitioning. Once we've done that, we're going to build tests based on choosing a value from each block that we've partitioned the domain into. And every possible value in a particular block is assumed to be equally useful for testing. And the key thing here is that's not just a coincidence. That's why we build the blocks the way we do, right? We want to partition the domain such that every value within a block is presumed to be just as good, just as useful, just as valid as any other value within that same block. If we feel like there are two values in the block and one of them is maybe a lot more useful than the other, or they might cause the system to behave differently, then we might want to repartition it, split that block somehow into 2 blocks and separate those things so that every value in each block is equally useful. And then when we apply that to testing, we're going to find our characteristics in our inputs, right? We're going to examine our system. We're going to identify the inputs. We're going to take those inputs, figure out what the input domain is, partition it into blocks, and then we're going to build tests by combining different values from those characteristics, from those blocks. And we can do that in a variety of different ways, and we'll look at a couple of those ways tonight. So what are some example characteristics? If we're looking at inputs to a system, we might say that, well, here's an input, and this input could be either null or non-null. I mean, that would be a way to characterize an input. Or if we had an input that was an input file, one way to characterize that input file might be its sort order. Is it sorted ascending or sorted descending or random value, or maybe there are other characteristics of the sort. If our input is, for example, what's an input device, right? What's the selected input device for this system? Then there's potentially a set of input devices, perhaps a DVD, CD, HDMI, whatever other input devices we might have. So when we're choosing partitions, at first glance, it seems very easy to choose partitions. In fact, it can be quite subtle, and it's kind of easy to get wrong. So let's think about that order of file. If we had an input file from the previous page and we said, well, it could be in ascending order, it could be in descending order, or it could be random. So is this partitioning, right? Our domain is the order of the input file. Is this partitioning complete? Does it cover every possible input file?
No, because there's like partial sorts and whatnot.
Partial sorts, so yeah, so a partial sort isn't really random, but it isn't really ascending or descending either. So that's a good potential one. Is it disjoint? Is there any overlap between these partitions? So it seems like there isn't. But what if we have a file that's got one element in it? Or, yeah, so if we have a file with one element in it, is it in ascending order? Well, technically, yes. And it's also in descending order, and it's also in random order. So really, these are not disjoint the way they're written. Now, we can rewrite them to make them disjoint, and we'll do that in a moment. What about an empty file? Is an empty file all of these things, or is it maybe not even any of these things? If there are no elements, it's probably not ascending or descending or random, right? So there are two cases. These are two cases that don't really fit these partitions, right? That make the partitions not look complete and disjoint. Perhaps there are others as well. So if the partitions aren't complete and disjoint, then basically we just haven't thought it through carefully enough. And like anything that we're designing, our partitioning should be reviewed, right? If we're doing this in a group development environment where we're doing things like design reviews and code reviews, well, this would be something that should be part of a test review, right? What are your partitions? And we should be making sure we're considering different alternatives and making sure we're coming up with a set of partitions that are complete and are disjoint. So now if we want to look at our overall approach to modeling the input domain, we've got 5 steps, and I've spread these 5 steps across kind of this range of, we have work that we're doing at the detailed implementation level, and then the work that we're doing at kind of a more abstract design level. And maybe these aren't really 2 separate boxes. Maybe this is a, kind of a shade of gray thing. But we're first going to start by identifying what are the things that we can test. From a perspective of unit testing, this is easy because every method is something we can test. From a system perspective, a system testing perspective, this might be more difficult, but it might be, for example, on a system that has a graphical user interface, it might be every time the user, hits OK or go or something to make the system take an action, we could identify that as a testable function. Then we're going to take our testable functions. That's very implementation level. And now we're going to start to abstract that. We're going to look at those testable functions and figure out what are the inputs to those functions and what characteristics do those inputs start to have. And when we start talking about characteristics, now we're kind of moving into the design abstraction level. Once we've got all the inputs and their characteristics, we're going to consider how to model the input domain. This is where we're doing things like partitioning our blocks. And we're very much doing this at an abstract level, right? This is without regard to the implementation of the system. Then we're going to apply a test criterion. I got the singular word here, so good, got the right word. We're going to take a test criterion and we're going to say, okay, we've got this input model, and now we're going to apply this input domain test criterion to it. And that's going to give us a set of test requirements. And then we're going to test those requirements, and we're going to refine those test requirements back at the implementation level into test inputs. Because, for example, if we had a test requirement that came out of this saying, test a file that's in random order, that's a perfectly reasonable test requirement. But I can't give the system an arbitrary, I can't give the system an abstract file that's in random order, right? I have to create a specific file with some specific data that satisfies that's in random order, right? So then that's that last process. We're taking those abstract test requirements and we're turning them into concrete implementation level test inputs that we can provide to our system. So let's take a little bit of a deeper dive into each of those 5 steps. In our first step, we're identifying the testable functions. So class methods, or individual functions. These are easy. Those are one testable function. Now, it's also true that methods in a class often have the same characteristics. So if I have a class that's managing students, for example, it might have a method, add a student to a class. It might have a method, remove a student to a class. They're both going to take student as an argument. So those 2 functions are going to have the same or very similar characteristics. So we can often build a domain model that we can share across different individual methods. Programs, when we look at systems as a whole, they have much more complicated characteristics. And then there may be many testable functions, right? So we may have input devices, we may have operating systems. So for example, if you're building a phone app, some of your characteristics to test for might be the underlying OS of the phone that it's going to be running on. Is this running on iOS? Well, which iOS version? They may be different. Is it running on Android? Well, every version of Android is different. So there may be many different and kind of less obvious and hidden characteristics that we need to consider at the system level. Whereas at the unit level, unit testing, all of those testable functions are usually pretty obvious. So then we're going to find all the inputs, parameters, and characteristics. So this is often a straightforward process, right? We can often, to find the inputs, we can often very simply look at the function call. Okay, this function call takes a student object and it takes an action object. Okay, well, I know what both of those are. It's very specific. But we may look at those values as we start to partition things. Okay, well, what do we care about a student? right? What are the variables within a student that we might care about? Are there relationships between those variables that are important to us? Are there special cases that we want to make sure that we're talking about, that we're considering? And very often, especially at the unit testing level, things like 0 and 1 and null, those are very typical special cases that we want to make sure we're considering. For unit testing, we're going to use the program source code to find the inputs, but we're not going to use the program source code to decide how to split them up, right? How to partition them. So a function might take an integer and it might say, you know, if the value is less than 10, then do this, else do that. Well, we don't care about that. We care that it's an integer. But we want to then break up the partitions based on what do we know about this integer? What's this integer's intrinsic meaning? Is it the temperature, right? The outside temperature? In that case, I might want to have something that's below freezing, above freezing, and really hot, right? I don't necessarily care about what the implementation wants to do. I want to break up those partitions based on our knowledge of the input domain. And so here we're transitioning from the implementation level to the abstraction level. And now we're going to be modeling the input domain. We're going to do this strictly at the abstract level. So we're looking at the parameters, right? What are the inputs? What are the variables? What are their characteristics? How do we break those up? How do we characterize the inputs? How do we partition them into a set of blocks? And then with each block representing a set of values. This is probably the hardest part of the process. It's certainly the most creative part of the process. It's certainly the part of the process where there's room to do things differently. One of the challenging things about input space partitioning is that there's usually no right answer. Or let me rephrase that and say there's usually no single right answer. There are often a collection of equally good or nearly equally good answers. There are still bad answers, but there's not always one right answer. There are different ways to approach the problem and different ways to partition a system that are equally valid. Then we're going to apply a test criterion to come up with test requirements based on blocks of those partitions. And our test input is typically going to have one value for each parameter, right? Each test is going to have one value for each parameter. And it's going to use one block from that parameter. Typically testing all the combinations of everything, right? I want to test all of the combinations of all of the blocks of all of the parameters. That's usually infeasible. It's usually impractical because the combinatorial number is usually too big, but it's also usually technically infeasible because often one value in one block will require or preclude, right, prohibit values from another block. And we'll see that as we start going into some examples. So this is also at the design abstraction level, and the output at this level is a set of abstract test requirements, right? Test requirements that specify what block I want to use for each test. And then our last step is refining those combinations of blocks into test inputs. So we're going to take a block and we're going to identify a specific value within that block so that we can come up with an executable test. And there are some tools out there, and we'll be experimenting. We'll be talking a little bit about the tools today, and actually your next assignment, assignment 4, will be using a test optimization tool that will help you pick appropriate combinations of blocks and appropriate data from within each block. And this step returns us back to the implementation level, because at the end of this, I have specific tests with specific inputs that I could provide to my system, right? So my next step after this might be, okay, now I'm going to go to JUnit and I'm going to implement the test. And I know what to do because I have specific values now. So there are two basic approaches to building your input domain model. There's an interface-based approach and a functionality-based approach. In the interface-based approach, we're really going directly looking at the direct inputs. What are the individual inputs? And I only care about them one at a time. I'm going to look at the inputs in isolation. This is a pretty simple approach, but it's not always the best approach. In a functionality-based approach, I'm going to kind of look at a behavioral model, right? What's the behavior of this system, and how do the parameters, how do the inputs interact? And what are their interesting interactions that I want to think about? That might result in better tests than an interface-based approach, or it might result in fewer tests that are just as good, which is another way of saying better tests. So in an interface-based approach, really, we're just going to take a mechanical approach. We're going to look at each parameter, each input in isolation and figure out how should we break this up and what should our values be. And we're going to ignore the relationships between the parameters. Let's take an example. All right, we have this function that we're going to be using for a couple of examples. Triangle. And we give the triangle, we give the length of 3 sides of the triangle. Now note that the 3 sides are all in integers, so that limits us a little bit about exactly what triangles we can specify, but integers make life easier for us, easier to test. So we're providing 3 integers, the length of side 1, the length of side 2, the length of side 3, and this class is going to come back and tell us what kind of triangle it is. It's either a scalene triangle where all the sides are different, or it's an isosceles triangle where 2 out of the 3 sides are the same, or an equilateral triangle where all 3 sides are the same, or an invalid triangle where those 3 lengths don't actually make a triangle, right? So like 1, 1, 5, I can't make a triangle out of those 3 lengths. So we're going to, in our interface-based approach, we're going to look at our inputs and we're going to consider them individually. Now in this case, the types, the data types of the sides are identical. The semantics, the meaning of each side is identical, right? Side 1 means the same thing as side 2, right? We're measuring the same kind of thing. So that suggests that our input domain model is probably going to be the same for each of these 3 inputs. So a possible characteristic for how to characterize the input would be, well, what's the relationship of the side to 0? How does the side length compare to 0? This might not be a great characteristic, but it's a potential one. And so we'll start with that as our example. And I might think that, well, if my characteristic is the relationship of side to 0, I have 3 characteristics, right? I have the relationship of side 1 to 0, I have the relationship of side 2 to 0, and the relationship of side 3 to 0. And I might decide, at least initially, okay, I'm going to break that characteristic, right, that domain, I'm going to break it into 3 blocks. And my 3 blocks are going to be greater than 0, equal to 0, or less than 0. That's not an unreasonable way to break up an integer input. It's maybe a little simplistic, but it's not an unreasonable place to start. So that gives me a maximum possible number of tests of 27, right? Because I have 3 possible blocks for side 1 times 3 possible blocks for side 2 times 3 possible blocks for side 3. So 27 tests, and they might look something like, if I pick greater than 0, greater than 0, greater than 0, right? 1, 1, 1, or 1, 1, 0, 1, 1, minus 1, 1, 0, 1. Well, you know, as we look at this, I didn't elaborate all 27 combinations here. And I just took a very simple approach in translating the block, right? I took a simple approach to translating the block to a particular test value. And I simply said, well, if it's greater than 0, I'm going to use 1. If it's 0, obviously I'm going to use 0. If it's less than 0, I'm going to use -1. You could use other values, right? Because our partitioning suggests that we think that any value greater than 0 is as useful as any other value. So you could have picked any value greater than 0. But I look at these tests and, okay, I didn't specify all 27 possible tests, but this test is valid. This one is invalid because a triangle with a side length of 0 is not a triangle, it's a line. You can't have a length of less than 0. That's an invalid triangle. So really, I end up with 1 valid triangle and 26 invalid triangles. And it's nice to test invalid triangles and make sure that our code works correctly for that case. But this kind of suggests that our input domain model maybe isn't a very good one, since most of the resulting tests are invalid. So I might decide to refine that. Okay, I'm gonna refine my model a little bit. I'm gonna add a special case of length equals 1. So I changed my initial block, which used to be greater than 0. I changed that to greater than 1, and I added a block on the end for 1. So now I've made a few more possible tests, right? There's a maximum possible tests. Maximum number of possible tests is 64. And I have a few more values that are valid. Overall, is this a lot better? Well, I got more tests. It's not really clear that the tests are a whole lot better. They're perhaps somewhat better because I can see I've got a little more variety. I have more tests that are probably going to be valid, so that's a good thing. But overall, maybe this approach of characterizing the length of each side with respect to its kind of absolute number maybe isn't that good an approach. So let's try a functionality-based approach instead. When we're taking a functionality-based approach, we're going to identify characteristics that are kind of in the domain of what we're trying to do, right? They're a little more meaningful to what the problem is. This means that it requires a little more design effort. It means that it requires us to have a little more domain knowledge and a little more semantic knowledge about what the arguments mean and what we're trying to do with them. But it allows us to use relationships between the parameters, which we couldn't do before in our simplistic interface-based approach. We can also do modeling more based on the requirements rather than based on the implementation. So let's take a look at an example. If we think about triangle again, well, really, when we think about side 1, side 2, and side 3, it's all 3 of those parameters together that really specify what kind of triangle it is. So I could set up an input domain model that'll combine those parameters. And so I've got a characteristic that's kind of an abstract characteristic. It's not the length of a side. It's, well, what kind of triangle do I want to test? So type of triangle. And then I might take my characteristic, type of triangle or triangle classification, and I might break it up into different blocks, right? Well, I want to have a scalene triangle. I want to have an isosceles triangle. I want to have an equilateral triangle, and I want to have an invalid triangle. So is this complete? And is it disjoint? And the giveaway is kind of on the screen. It's probably complete in that there's no kind of triangle that doesn't fit into one of these blocks, but it's not disjoint because technically an equilateral triangle with 3 sides the same is also an isosceles triangle with 2 sides the same. So we need to refine our blocks just a little bit and change isosceles to isosceles but not equilateral. And now it's arguably, probably disjoint. So this results in only 4 tests, right? If I wanted to satisfy all combinations, I'd have to have a scalene triangle, an isosceles but not equilateral triangle, an equilateral triangle, and an invalid triangle. So that's only 4 tests, which isn't that many. Of course, I can have as many scalene triangles as I want and as many equilateral triangles as I want. But the nice thing is, all of these tests are at least, reasonably valid values. Yes, this last one is going to be an invalid triangle, but all of these values are realistic. So that's probably good. Or if I wanted to test values that specifically were invalid, I might need to have some special cases for that. So let's talk about different criteria that we can apply to input space coverage, right? If we've made our input domain model and we've created our blocks, what kind of coverage criteria can we use to take those blocks in that model and turn it into abstract test requirements? And the most obvious one is, well, just pick all the combinations, right? All combinations of blocks from all characteristics. So that can be a relatively large number of test requirements. It's essentially the product of all of the characteristics in each block, right? So for triangle, if we go back to the data model where we said length of each side is greater than 1 or 0 or less than 0 or 1, then I have 4 blocks in the first characteristic times 4 blocks in the next characteristic times 4 blocks in the third characteristic. That gives us 64. And of those 64, only 8 of them are really valid combinations, which again suggests maybe this isn't a great partitioning, but all combinations would give me 64 combinations. For this relatively simplistic thing that we're testing, is 64 too many test cases? Well, I mean, arguably you can never have too many test cases, but it does kind of seem like a lot, right? Requiring you to write 64 test cases for this simplistic thing seems like a lot. So let's look at an abstract example. If we had a system where we've identified 3 characteristics, the first characteristic has 3 blocks, the second characteristic has 2 blocks, and the third characteristic has 2 blocks. Now we want to produce all possible combinations. So we have A1, B1, C1, A1, B1, C2, A1, B2, C1, A1, B2, C2. You can work your way through this and you can see how we've basically just iterated through each one, right? We started with A1, B1, C1, we iterated through all the C's, then we iterated through all the B's, then we iterated through all the A's and did it all over again. So it's all possible combinations. So what if we look at triangle type? This is a little bit more of a concrete example. In triangle type, we've got the length of side 1, length of side 2, length of side 3. We identified 4 blocks for each of them. At least one of our data models had 4 blocks for each of them. And so here we've got the same thing, right? It's just the complete product of all of these. So minus or greater than 1, 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 0, greater than 1, greater than 1, less than 0, etc. We're just going to iterate through all of the combinations. And that gives us our 64 combinations. I mentioned earlier that all combinations is often infeasible in practice. And it's often impractical because there's just so many. So what if we wanted to reduce the number of test requirements? Well, we could take this each choice coverage. In each choice coverage, we have to use one value from each characteristic in at least one test. So this is really going all the way the other way. This is a very minimal set of combinations. So the number of test requirements is simply the number of blocks in the biggest characteristic. So for triangle, with this data model, right, the characteristics all have 4 blocks. So we just have 4 required tests. We could take all the greater than 1, all the equal to 0, all the less than 0, all the equal to 1. These aren't particularly effective tests, and there aren't very many tests. So this is maybe not a super useful criterion. So let's look at an example. If we go back to our abstract example, we've got characteristics A, B, and C. A's got 3 blocks, B and C have 2 blocks. All I need is for each thing, right? Each of these blocks to appear once. So I create a first test that has A1, B1, C1. And then I create a test that has A2, B2, C2. And then I need to get A3 in here because I haven't used A3 yet. So I need a test with A3. But I could use any values for B or C because all the values for B or C have already appeared. So we'll just reuse whatever we want to use. We can select them randomly. We can select them based on what the easiest one is to implement. But 3 tests uses all of these values. If we look at triangle type, again, we have to use all of these values. So we could just pick all of the greater than 1, all of the 0, all of the less than 0, all of the 1. That would be this test case. Or we can mix and match them. We could pick greater than 1 with 0, with less than 0, and then just kind of go down the list and pick all the other ones. And there are lots of different combinations. But any one of these 4 tests with 13 possible more sets of 4 tests would satisfy each choice. All it requires is that we use each of these values at least once. So another technique we can use, if we feel like all of the values appearing once just doesn't give me very good tests and doesn't give us very many tests, but all possible combinations gives us too many tests, we could look at pairwise combinations or pairwise coverage. In pairwise coverage, we want to use every block for each characteristic and combine it with every block of every other characteristic, right? So every 2 blocks, all the combinations of every 2 blocks. What does that really mean? So the number of tests is going to be smaller. It's going to be at least the product of the 2 largest characteristics. So if we go for triangle here, it's going to be at least 4 times 4, 16 tests. That seems like it's maybe a good, in good range. If we give some example values, we maybe have some more interesting tests than we had before. So it's looking positive. One of the downsides of pairwise coverage is that computing every possible pair can be a little hard to do manually, especially as we get into more complex test cases, right? More complex characteristics. It can be very hard to compute manually. But for a simple example, let's take a look. So if we go back to characteristics A, B, and C, where A has 3, B has 2, C has 2, this is a set of tests that provides every combination, right? So A1 and B1 is in here somewhere, and A1 and B2 is in here, and A1 and C1 is in here, A1 and C2 is in here, A1 and B1 is in here, A1 and B2 is in here, A1 and C1, A1 and C2, B1 and B1 and C1, B1 and C2, right? All of those combinations, every possible pair of combinations is in here. And where I have a star, it simply means that it doesn't matter. Right? It doesn't matter what you've picked, right? You don't have to, you could pick C1 or C2, it doesn't matter. And so we can further optimize this with a little bit of clever reuse. We could reduce this to 6 tests. And these 6 test requirements satisfy all of these. This is kind of the hard part, right? This isn't that hard to do. This combination part, right? Reducing it into a very efficient test set, that can be the hard thing to do. Fortunately, there are tools that will support us in doing that. So if we look at triangle type, this one's a little harder to figure out, but every possible combination of side 1 greater than 0 with all the values of side 2 and side 3, for example. Those are all in here. We can satisfy that with, what did this end up to be, 4, 8, 16 tests. So this has every combination of every side 1 with every side 2, and every side 1 with every side 3, and every side 2 with every side 3. There are other combinations that you could make that could satisfy this, but this set of combinations is one of the solutions. Again, this can be really hard to do manually. And so except for trivial cases, you will not be asked to do this on quizzes or on the final exam. We can also extend pairwise. Well, if we thought every combination of every 2 things was good, what about every combination of every 3 things, or every combination of every 4 things, or every combination of every 5 things? And we can use that to basically take our dial and turn up our testing dial and get more and more, excuse me. We can use that to turn up our testing dial and get more and more tests if we feel that we want more tests. If you thought pairwise was hard to compute manually, 3-wise or 4-wise or 5-wise is very, very hard. And now you're really absolutely into the realm of using tools to do this. So what's the number of test requirements? Well, it's at least the product of the T, whatever we've chosen for T, largest characteristics. Now, the interesting thing to remember here, an interesting thing to keep in mind, is that if we set T equal to the number of characteristics, then T-wise is equivalent to all combinations. So if I have 3 characteristics and I want 3-wise testing, then that's equivalent to all combinations. If I have 3 characteristics and I want 4-wise testing or 5-wise testing, I can't do that because I only have 3 characteristics. We can't get any more complicated than all combinations. So as we take T, right, that number of combinations, as we increase it, statistically, we do find more faults. We get dramatically more tests, and we do find more faults, but we don't find a lot more faults. So this is from a National Institute of Standards and Technology study that looked at 5 different kinds of systems, right? A medical device system, a web browser, some server software, some NASA software, some network security software. It doesn't matter what the software was. The key thing is that they took very different types of software. And they did testing, and when they looked at setting T to 1, which is each choice, they found a certain number of defects. And when they set it to 2, which is pairwise, they found a lot more defects. And as they turned it up to 3 and 4, they didn't really find that many more defects. So doing pairwise or 3-wise really got them just about to the maximum number of issues that they found with a lot fewer tests than 4-wise or 5-wise or 6-wise. So you definitely have this diminishing returns thing, right? So each choice, not very effective. Pairwise, pretty effective. 3-wise, even better. You know, all combinations, well, it's a little better, yes, but for dramatically more work. So we have one more approach that we're going to talk about. And this one we're actually going to use a lot because it's very, very useful. Base choice coverage. So in base choice coverage, we're going to apply some domain knowledge to the program to identify some important values. This is a really nice coverage criteria that's very effective at finding issues with a very, I guess I'll say, comparatively small number of tests. So when we're looking at, let me back up a second. When we're doing base choice coverage, we're going to choose a base test requirement, right? We're going to choose one block from each characteristic and say, that's my base test. And then we're going to vary that one characteristic at a time to create all of our additional tests. So the number of tests is the number of one base test plus the number of characteristics in the other blocks. All right, let's dig into that a little bit. First, we want to choose a base test. Our base test must be feasible. That means that all of the values, all of the blocks that we pick for our base test, they have to be compatible. They have to give us a good, valid test. Our base test is typically going to be set up by, the most likely or most common values, right? What's the most likely way this thing is going to be used? That makes a good base test. Or the simplest values, the smallest values, or the first values in some logical ordering, or best of all, happy path tests, right? A test where this is kind of all expected input and everything should work fine. That makes a great base test. And choosing your base test is a crucial design decision. So when you're doing this for real, you should be documenting why you chose the base test that you chose. And if you choose poorly, then that can result in lots of infeasible combinations, lots of additional tests that can't be implemented. And if you have a lot of infeasible tests, that should suggest to you that maybe you should go back and think about your base test a little more. So let's look at an example. So in the abstract ABC example, where none of these things matter, we're going to choose a base test, and we'll simply choose a base test by picking the first values. So our base test is simply A1, B1, and C1. And because this is fully abstract, we don't have any reason to believe that this is a better or worse test than anything else. So we've simply chosen the first ones. And now we're going to create some additional tests. We're going to create some additional tests by making variations on A. So we're going to hold B and C constant, and we're going to rotate through the rest of A. So we started with A1, B1, C1. So we're going to substitute in A2 and then substitute in A3 while we hold B and C constant. And that's going to give us a set of variations for A. And then we're going to hold A and C constant and iterate through the other choices for B. In this case, there's just one other choice for B, B2. And then last, we're going to hold A and B constant and iterate through the different choices for C. Again, there's only one other choice for C, C2. So that gives us our variations on C. So now we've created 5 tests out of this. We've got our base test. We've got all the variations, the other values of A, all the other values of B, and all the other values of C. The important thing to remember here is that as we're building these tests, we're only varying one characteristic at a time, and we're holding the other characteristics constant. So let's look at that from the perspective of triangle type. If we look at triangle type, we could make a base test. What's our base test? Well, we should probably pick a happy path test, right? And 1, 1, 1, that's actually the only test with these values, or it's a simple test with these values that we know will be valid. So that makes a good base test. Then we're going to take all the variations of side 1, right? So we're going to go through the other blocks for side 1. Then we're going to go through the other blocks for side 2. Then we're going to go through the other blocks for side 3. In each case, while we're holding the other ones constant.
So each side corresponds to that parameter, right? Oh, I see you
Yes.
highlighted. Yeah.
Yep.
Okay.
Yep. So this is side 1, side 2, side 3. Right. So this row, we've basically gone through the other variations of side 1 while holding side 2 and side 3 constant, etc. So this gives us, a relatively small body of tests. And these tests actually seem kind of interesting. There are still plenty of invalid values, but there are some more valid ones. So this is maybe the most interesting compact set of tests from the things that we've done here. We can also extend base choice coverage to multiple base choice coverage. In multiple base choice coverage, we're going to say, I liked base tests so much that I'm going to pick more than one base test. I'm going to pick, for example, 2 base tests, and then we'll work from there. Let's see what that looks like. I don't really care about the number of base tests. So for example, we might pick a first base choice, or first base test, A1, B1, C1. And then we'll do our variations on A, and we'll do our variations on B, and our variations on C, just like we did before. Then I'm going to pick a second base test. And let's say that for whatever reason, I feel like A3, B1, C2, that's a really interesting, good base test. Great, so that'll be my second base choice. Now I can actually go back and I can say, I don't need this A3, B1, C1 because I used A3 in my second base test. And I don't need this A1, B1, C2 because I used C2 in my second base test. I can't throw out this one because this was my first base test. I can't throw that out. I got to keep that. And now given this base test, we can do our variations on that. So we can say, okay, here are our variations on A. Oh, but I don't actually need this one with A1 because A1 was already another base test. So I can optimize and get rid of that. But A2 I want to keep. And then I can do variations on B, and I can do variations on C. And again, I can say, I don't really need this variation on C because C1 was already part of the other base test. So I can kind of clean up those things that are duplicates. And you can see how you can put together, a really good set of tests here, especially if you've got kind of a complex system. You might think, well, there's more than one common set of inputs or more than one typical thing that I should test. So let's identify several base tests and then build up all the supporting tests around it. Okay, I already talked through all my bubbles. So what does that look like with triangle? Well, I might decide for triangle, I want 2 different base tests. I want a base test where all the sides are 1, and I want a base test where all the sides are greater than 1. So we'll create our first base test. We'll do the variations for side 1, variations for side 2, variations for side 3. Then we'll do our second base test. At that point, I can go back and I can clean up. All right, I can get rid of some of these variations because these are values that appear in the second base test. And then we'll do the variations of side 1, side 2, and side 3, cleaning those up as we go because we've already used those substitutions in the first base test. Okay, getting towards the end here. We can have constraints among the characteristics because some combinations of characteristics are infeasible. Now, I know that these 2 things did not appear together in any, right? The less than 0 and scalene, they were in 2 different input domains. But for example, you couldn't have a side less than 0 and have a scalene triangle. Because if a side is less than 0, then it has to be an invalid triangle. So we can have these kind of constraints. And in general, there's going to be 2 different kinds of constraints. The first constraint is that if I have a block from one characteristic, it cannot be combined with a particular block from another characteristic. Alternatively, if I have a block from one characteristic, it can only be combined with a specific block from another characteristic. Really, those are 2 ways of saying the same thing. Because if I have a block that cannot be combined with each of the values from one characteristic except for one, then I have the other one. So what do I want to do if I'm building my tests, whether it's each choice or all combinations or pairwise or base coverage? What do I do if I run into a set of test requirements where I have a combination that's infeasible. Well, if I'm doing all combinations or pairwise or T-wise, then I'm simply going to drop the infeasible pair, right? I'm just going to take that, okay, that test is infeasible, delete it. But if I'm doing base coverage or multiple base choice coverage, then I want to make some other subtle change to that test case to try to find a feasible combination if I can. So for example, if I had a base case, a base choice case of, you know, block one, and block one. Nah, I'm going to leave that aside because we've got an example for it later. And it's going to be easier to understand in an example than me kind of talking about it without a slide. All right, so let's look at a particular example and let's look at this input domain and let's consider what the constraints are. Yeah, can I explain what infeasible means? Yeah, infeasible in this context means that the two combinations can't go together. I can't produce a test. All right, I can't have a valid test, a set of inputs that are like that. So we'll see some infeasible test cases here, and I think it'll become a little more clear then. But basically, we're saying that there are combinations between the characteristics that can't be legitimately combined. All right, so I've got this function find element. I give it a list, I give it an object, and it tells me whether the object is in the list or not. And it might throw null pointer exception if the list is empty, or if the list is null, or if the element is null. Otherwise, it'll return true or false. So I could do an input domain analysis of this. I could look at it strictly from an interface perspective, or I can look at it from a functional perspective. And here I'm going to look at it from a functional perspective. I'm going to consider what are we trying to do here and what are the combinations and the values that matter. So my first characteristic is, what is the size and contents of the list? So question in there, I thought characteristics pertain to the inputs, not the desired output. They can pertain to the inputs and the relationship between the inputs. The relationship between the inputs can be related to the desired output. So earlier when we were looking at triangle sides, when we took our functional approach to triangle sides, we said, well, really, there's a relationship between the side lengths. And that relationship is that the triangle is scalene or isosceles or equilateral or invalid. And so we used that as our characteristics. In that case, it just happened that those characteristics mapped exactly to what the output of the triangle type was going to be. That doesn't have to be the case. It doesn't have to map exactly, but it can. So here we're going to look at what's the size and the contents of the list. Well, the list could be null, and I know that that's an interesting block because if the list is null, then we want to do something in particular, return null pointer exception. The list could be empty. The list could have one element in it. The list could have more than one element in it, and they could be unsorted and different. The list could have more than one element and they could be different and sorted, or the list could be more than one element and they could be all the same. Now, for the moment, we're going to assume that this is complete and disjoint. We might have another characteristic, and that characteristic is, does the element that we're passing in, does that match anything in the list? And because we're taking a functional perspective here, you know, what matters to this program, this would be a reasonable thing to do. So we could say, well, maybe the element's not found. That's a case I'd like to have. Or the element's found once. Or the element's found more than once. Those seem like three reasonable things that we could do to decide whether the element matches the list. But that's going to give us some infeasible combinations. Why? Well, for example, we can't have characteristic A block 3, which is size equals 1, with characteristic B block 3, element found more than once. Because the element can't be found more than once if the list only has one element in it. So that combination is infeasible. There is no way, if I gave you those test requirements, build me a test where the list has one element in it and the element is found more than once. And you can play with JUnit as much as you want, but you can't make a test that meets that. So that test is infeasible. How about AB6 and BB2? AB6 says the size is greater than 1 and they're all the same elements. And BB2 says the element is found once. Well, if the element is found at all, and all the elements in the list are the same, then the element has to be found more than once. So that's an infeasible combination. I won't go through all of these. I don't think I have any more highlighted. I guess I do. Maybe I will go through all these. AB2 and BB2. If we have a list that is size 0, then we can't have our element found once. We also can't have our element found more than once. AB1, if our list is null, we can't have our element found once or more than once. It has to not be found. So those are infeasible combinations, right? These are cases where you couldn't possibly write a test for this. You just can't do it. If you're taking a functional approach to your input domain modeling, you are typically going to find infeasible tests, infeasible combinations. If you're taking a strictly interface-based approach, like where we looked at triangle and said, well, you know, it's the value is less than 0 or it's 0 or it's greater than 0. Well, you can write tests for all those things, so there's no infeasible combination in that case. So typically, if you're taking an interface-based approach, you're going to have few infeasible combinations. I will not guarantee that there will never be any, but relatively few. If you're taking a functional-based approach, you're probably going to have more. So the method itself doesn't seem to distinguish. That's true. The method doesn't distinguish that. The method just says, I found it or I didn't find it. However, we could still build this, right? We could still build this because it is logically appropriate to the concept of having a list with elements in it. Now, should we? I don't know. I mean, there may or may not be a compelling reason to build this particular data model, but the data model is valid because conceptually, I could have the same element appearing more than once. Whether or not we want to implement that, right, that's going to give us more test cases. Are those test cases interesting? It depends, right? For what we know about this method right now, I don't know that those test cases would be all that interesting. But if we started to look for something like a find first or a find last, then it becomes very interesting whether or not there's more than one element. So maybe having a find first or find last element would be a more interesting case, because then that really makes these necessary to our testing. All right, so you'll start to see every week as we talk about different types of coverage in our category, we're going to talk about how they subsume each other. All combinations subsumes everything. If I satisfy all combinations, I am guaranteed to have satisfied T-wise and pairwise and each choice and multiple base choice and base choice. Because if I've satisfied all combinations, I've done everything you can do. There are no other test cases you could come up with. If I've satisfied T-wise, where T is greater than 2, then I've guaranteed to have satisfied pairwise. And if I've satisfied either of those, I've satisfied each choice. If I satisfy multiple base choice, then I've satisfied base choice. If I satisfied base choice, I've satisfied each choice. But there's no relationship between the two sides here. If I've satisfied base choice, I have not necessarily satisfied pairwise. And if I've satisfied T-wise, I have not necessarily satisfied base choice. I don't know. Coincidentally, maybe I did, but there's no guarantee that I did. Therefore, there's no subsumption relationship. All right, so a little summary of input space partitioning, input domain modeling, whatever you'd like to call it. All those names are valid. It's pretty easy to do this, right? It's pretty easy to build a domain model, to take up blocks, to apply criteria, to build test requirements. Even if we don't have automation, it's pretty easy to do. If we want to do pairwise or T-wise, maybe we need to have automation because that's hard to do by hand. But overall, it's fairly easy to do this manually. There are some convenient ways to increase or decrease the number of test cases. If I do base choice and I decide, you know, I need more test cases, I can very easily switch to multiple base choice. Just pick another one that makes more test cases. If I've done pairwise and I want more test cases, I can turn it up to 3-wise or 4-wise. I can get more test cases. It's applicable to all levels of testing. This is appropriate for unit testing, integration, system acceptance. Every level of testing you're doing, you can use this approach. And generally speaking, it's based on an analysis of the inputs to the program, not the implementation of the program. So it's fairly simple, pretty straightforward. It's highly effective. And this is a very, very widely used approach to testing. All right, that takes us to the end of our input space coverage. So questions or discussion here before we go to break? All right, so we're going to get into our class activity for this week. I'll brief it out first, then we'll send you on your way. All right, so we have this method, this intersection method. The intersection method takes two sets and it returns a set that is the intersection or the overlap of those two sets. We'll also throw a null pointer exception if either of the provided sets are null. So we might come up with the following domain model. This is going to be the domain model that we start with. We've identified two possible characteristics. The first is the type of set one. Is set one null, or is it the empty set, or does it have greater than or equal to one element? And then we have the relationship between set one and set two. Are they the same set? Is set one a subset of set two? Is set two a subset of set one, or set one a superset of set two, if you want to look at it that way? Or are they disjoint? There's no overlap between them. So that's the domain model that we're starting with. So here's the first activity. If we take that domain model as it's shown, and we wanted to apply base choice, how many test requirements would result? And give an example set of test requirements. If we wanted to choose pairwise, and you know what, I'm going to modify this slightly. Well, nice try, I was going to. I'm going to take away the provide a set of test requirements. Okay, so if we applied base choice to the partitions as they're shown, how many test requirements would there be, and give a set of test requirements? If we applied pairwise, how many test requirements would there be? if you've got the opportunity, you know, if you have the time, then great. I'd love to see your suggested set of test requirements, but that's not necessary. And then I want you to consider, are the characteristics for A complete and disjoint? Why or why not? And if you think they're not, then propose a fix. And is the partitioning for characteristic B complete and disjoint? Why or why not? And propose a fix. All right, and then I've got kind of page by page, you know, working slides that you might wish to use in your group or not. But there we go. So base choice, number of tests and some example tests. Pairwise, number of tests is sufficient. Is characteristic A complete and disjoint? Is characteristic B complete and disjoint? Any discussion before we go? All right, I'm going to make this 25. I think I'll make this 20 minutes. I'll make it 25 minutes. And then we'll come out and we'll talk about what we found. All right, now we're back. All right, so let's go through and let's see what folks did. So it's, this week we're going to start with Ravenclaws. So Ravenclaws, can you show us what you did for your base choice criterion?
I can talk about it and not share my screen, I guess.
That'll be fine.
Okay. For a base choice, we just chose for characteristic A, we chose block 3, so greater than or equal to 1 element. And then for characteristic B, we just arbitrarily chose block 4, so they're disjoint. So after that, that's A3, B4. Then we vary characteristic A. So from that, we get A1, B4 and A2, B4. And then after that, we varied characteristic B. So we got A3, B1, A3, B2, and A3, B3. So if I know how to count, that's 7. And I guess I already listed out the exact set of TRs.
Yeah. Okay, good. So did I do the same as you did? Actually, it turns out by chance I did. So I picked exactly what you said, and I picked greater than or equal to 1 for set 1, and the 2 being disjoint. Other groups that I was talking with made other choices for B, for characteristic B. And, you know, I think other choices for characteristic B are fine. This one maybe is a little better because there might be a few fewer infeasible test cases. But again, it's a very reasonable thing to do. Any of the Bs would be a very reasonable thing to do. It would make a decent happy path. So, all right, thank you. Nice job. So did anybody compute the number of pairwise tests required, or the number of pairwise combinations?
Anybody just in Ravenclaw or?
No, anybody.
I'm not sure if this is correct, but Muggles came up with 9 because we said that the maximum number of test cases could be 12, because it's 3 times 4, but then we found 3 infeasible, so we dropped those and we got 9.
Ah, okay. So how many you get that are infeasible depends on what you pick. By the formula that we were using, the maximum number of test cases would be 12. Now, it turns out that we're doing pairwise, and there are two characteristics. So in the case of pairwise with two characteristics, it's the same as all combinations. So you would actually end up with all combinations, which could be 12. Now, as you said, we could go through here and we might be able to identify infeasible combinations and knock those out. So actually getting down to 9 is that's a pretty reasonable and really believable thing to do. So good job. All right, so we're going to go to Slytherins next. And so Slytherins, if we look at partition A, right, type of set 1, is that complete and disjoint?
We have the answer of our answer is yes, and they are complete and also destroys.
Complete and disjoint. Okay, so I agree. As far as I could think of, there are no other possible values. I can't have a set that's not null or not empty or doesn't have more than one or more elements, right? So it's complete. There's no other set I can think of that wouldn't match one of them. And it's disjoint because, well, these are all very different. I can't match both of them at the same time. All right, so that's a fairly simple one. Let's go on to Gryffindor now. Gryffindor, for characteristic B, are they complete and disjoint?
So we thought that it was like complete because like the 4 possibilities kind of cover all types of input. Like you can have either the same set or where one set, you know, is a subset or superset of the other set, or there's like nothing in common. We thought like that kind of covered the different types of input we would get. But in terms of disjointness, we were thinking about the case like where if you have like 2 sets, like how would you handle like the case of like a null set and like an empty set? Like how would you consider whether or not they're disjoint or like the same set or stuff like that? So we weren't really sure.
Yeah, so
the disjointness.
So I think you're thinking if a set was null, then does it maybe fit more than one of these?
Mm-hmm.
Okay. I think you're on the right track there. Anybody else want to contribute here, whether you feel that this is complete or disjoint?
I think it's neither. Well, we came up with that it's neither of those.
Okay. And why do you think that?
Well, it's not complete because it's missing the case, like a Venn diagram case of like when we have overlap, but it's not like a subset or not subset. And then for why it's not disjoint, because there's like proper subsets versus subsets, and subsets could have the same set as well.
Okay, very, very nice work on the Slytherins here. Not only did you catch the partial overlap one, right? They're not disjoint, but they're not the same and they're not subsets either. But you also caught the more subtle one, that subset and proper subset are not the same thing. So nice work there. So let's take a look at what we might do. Right? It's not complete because it doesn't handle the possibility of partially overlapping sets. And it's not disjoint because by definition, identical sets are subsets of each other. And the empty set matches all the partitions. So if I had set 1 and set 2 both being the empty set, then kind of by definition, all of these are true. They're the same set. The empty set is a subset of another empty set and vice versa. And the union of 2 empty sets is empty.
Can I interject here? You wrote, you gave the proper subset symbol. So those are actually are disjoint.
So this is not the proper subset symbol. Or is it?
I thought it was the one that has underlined, but maybe
The one with a bar underneath it is the improper subset because it's like It's kind of like the or equals to symbol.
Well, we will do what everybody does and ask the Google, as my daughter likes to say. Is it possible that after all these years?
Yeah, I looked it up just now. I think Kyle's right.
Well, let's see.
Because I guess the line will say like it's
right.
fine if they're, yeah.
I'm going to have to look into that, Kyle. At a glance, I'm not sure what the answer is,
Well,
but I'm going to have to look into that.
yeah, the symbol is for the proper subset, but even then, aren't we missing? It's still just not disjointed, but actually,
All
yeah,
right,
it's still
so-
disjointed. Yeah.
So I'm going to continue for the moment with the caveat that I'm perfectly willing to backtrack on this if I haven't said the right thing. All right, so we know it's not complete. How are we going to fix the completeness problem? Well, we're going to add another partition, right? So we'll come out here to number 5, and we'll add a partition where the two are not subsets of each other, and the union of the two is not the null set, or in other words, there's a partial overlap. Now we think we have a complete. We'll assume for the moment, as I said, that these symbols really do mean a subset, but not necessarily a proper subset. Now we think we are complete, but we know that we're not disjoint yet. So we're going to change this to proper subset. Now, that's my interpretation of the proper subset symbol, or what I believe the proper subset symbol is. Again, I'm willing to go back and double check on that. So now if we've got these as proper subsets, now I think we pass the disjointness test as well. And that, I think, is exactly what, sorry, there's too many people on the screen and I didn't catch who was speaking before. Momal, I think it was you. You were giving us the description, yeah. So I think that what I've got here is just what you were saying. But that fixes that problem. But what about this case over here? We maybe, because we could have, if I go back to what we had, if set 1 and set 2 were both null, or excuse me, were both empty, then they're the same set and their union is disjoint. So we still have to fix that disjointness problem. So we'll come over here and we'll make this rather more complicated, but basically it boils down to disjoint non-empty sets. And then I think we finally fixed the disjointness problem, because now if the two sets are both empty, then they will only fit into B1. All right, so that takes care of the first exercise. Now we're going to jump into the second one. All right, we want to consider the constraints now. We're going to look at the constraints between the blocks. What constraints do we have? And what we'd like to do here for this exercise is look at all of the constraints using, you can either use your version, right? Or you can use the one that we just updated. Either one's okay. I would say for simplicity, use the version that you produced, that your team produced, right? The one where you were trying to solve disjoint and complete. Use that version and identify what are the constraints. So what values of A require or prohibit what values of B, and vice versa. If you've got time, then once you've done the constraints, let's look at some more base choices. What would be your new base choice coverage test requirements once you've put your constraints in place? All right, so I will make this, I'm just going to make this 10 minutes, which I realize 10 minutes is not very long. You're probably not going to get through the constraints and get to this, but you know, I want to have a chance to talk about what some of the results are before we finish tonight. All right, 10 minutes, off we go. I have been in on some good conversations here. At least a couple of different groups are really kind of having some good thoughts, some little bit deeper thoughts about, hey, wait, this isn't as obvious as it seemed at first, especially with respect to, okay, if set 1 is null, can I even compare it with anything here in B, or are all these just invalid, which then suggests that really this isn't complete after all? Or should I take a null set and just sort of treat it as if it was empty, in which case these do make sense? Both of those approaches are possibly reasonable things to do. But you know, I congratulate you for kind of catching on to, wait a minute, this is more complicated than it seemed at first. So I'm not sure where we left off. I think Gryffindors, I think you're up next. So what did you come up with for constraints? And what interpretation did you use to get there?
So for us, we looked at like the mathematical definition for sets, on like how to treat the null set, because that was the main focus of our discussion. So when we looked it up, it said that like a null set is like the subset of all sets. And I guess that's interpreting it to be that a null set is like similar to an empty set. And so we basically said that like A1 and B1 would be possible because you could have 2 null sets or like 2 empty sets and they can be equal to each other. And we also said that, let me double check which one it was. It was A1 and B2 is possible because you could have like a null set, which in this case you're treating like as the empty set, and you could have S2 be like a set that has, you know, more elements in it. So in that case, it is possible for S1 to be a subset of S2. And then we said that it wouldn't be possible for A1 and B3 to exist because if S1 is empty, like there can't be anything smaller than that. And then, yeah, and then for B4, and B5 we were still kind of a little stuck on those two, but we were considering that it is not possible.
Okay.
But we're still discussing it. Yes.
Okay, great. Good job. So how about Hufflepuffs? I don't think we've heard from you today. Do you have anything you'd like to add or any different interpretation on what you did here?
We kind of had the same approach as the previous group. We thought that A1 could be applied to B2. So we made like a conditional statement on that. So we put and not null to prevent that case.
Okay. Okay. Good. So I did take just a minute to go back and do a little research on subsets, and it turns out that there is inconsistent usage of that symbol. And so this clearly means proper subset, but it's unclear, and there's different usages for whether just the sideways U without a line under it. There's different usages and different interpretations of whether that means proper subset or not. So I'm not quite sure what to do about that in my slides, but I'll have to give that some thought. So
I will say, I think I know another class had the bar underneath it as a part, as subset or equals.
Yes. Yeah, the U with the bar underneath it, right? That clearly means proper subset or equivalent sets. And this with the bar and the slash clearly means just proper subset. The question is, what does it mean with no bar at all? And the answer seems to be the usage is inconsistent based on what source you look at. So something to think about for me to how to improve my slides. All right, so we're just about out of time here. I will go over just very briefly what I came up with here so that you can reference that and think about what you want to do with it. So I thought one interpretation, as I talked about, was, well, hey, if set one is null, then it doesn't even exist. So does it match any of those things? And I was kind of thinking, well, no, there really can't be a relationship to set two if set one doesn't even exist. So that led me to say an additional block here where if set one is null or set two is null, then I don't otherwise have a comparison. And then that led me to a bunch of, now I felt like I could do, constraints. The alternate approach that we talked about a minute ago where, okay, well, I'm going to kind of treat a null set as if it was empty and then these relationships hold. That's not necessarily wrong, and it's not necessarily unreasonable, and it's not necessarily going to give you bad tests. It's just a different way of looking at it. And this way is maybe more technically correct, especially from a Java perspective, where a null object is different than an empty set. But again, we're doing this work at the conceptual level, not at the implementation level. And I really think either one could work. But if we're an empty set, then we clearly can't have set two be a subset. If we're an empty set, then clearly there can't be overlapping. If we're the same set, then I felt like if we're the same set, the set couldn't be null based on the rules that I made up. Before, if set two is a proper subset of set one,
Professor, are you sharing your screen?
Maybe I'm not. If you're asking me, then I guess I'm not.
No, you know you weren't.
Sorry,
Yeah.
My apologies. All right, so here we go. So this is what I did. I added this block to deal with, well, what if one of the sets is null? Then if B4, if we're in B4, which is set two is a proper subset of set one.
What is that arrow notation?
This arrow?
No, up in the yeah,
This
that.
guy? That's OR, logical OR.
Oh. Okay.
So if we're in B4 where set two is a proper subset of B1, then that implies that it can't be, well, I think that's wrong. There's no not there. If set two is a proper subset of set one, then set one has to have one or more elements. So I got to get rid of that not and clean that up. But there you go, some example constraints. As we're after 7 o'clock, I will let you look at them on their own. I'm going to just briefly update this right now and get that updated version posted. And there we go. All right, so with that, we'll finish for tonight. Overall, really nice job, folks. I'm feeling like you did a really nice job on these exercises and that you really were kind of grasping not just at the kind of the high level, but you were really kind of able to dig down a little deeper and come up with some of the more subtle things here. So nice job. Test goes active now. Due as usual by the end of Thursday. Assignment 3 is due next week before start of class. And I think that's everything. And I'll chat with you on Blackboard. Have a good week.